Yes. All right. Okay. Okay. This one. Okay. Test 1, 2, 3. The sound from iPad. Right. The sound from iPad. This is the iPad. Okay. Is the iPad sound in? You need to check. Okay. Test 1, 2, 3. Test 1, 2, 3. 1, 2, 3. Test 1, 2, 3. Test 1. Test 1, 2, 3. Okay, great. Okay, just from 1750, right? 1750 and 120, it's gonna be 1910, right? It's 1910, and we're gonna leave these. It's at 19 and 0. Okay, and 1 0. Okay. I hope that everything is fine. Good afternoon, everybody. Welcome you to SCI33206 physics number 5, which is part of the physics college subject at the Suankularb Wittayalai School in Bangkok, Thailand. This is the compensation lecture that we were missing in the last week, right? You have already seen the photon energy, right? Actually, photon is already energy. Photon is a kind of energy. Actually, the word energy should be skipped. Okay. The result in 7 is known as Planck-Einstein relation, and the photon can give all its energy HF to a single electron, okay, in the metal, and that's why we have this experiment. Okay, the energy by photon is absorbed by the atom in the metal. And the work function, right now we will talk about the work function, which is denoted by the variable theta. Okay, variable theta, and it represents the minimum energy with which an electron is bound in the metal. So if you can destroy the bounding, the attractive force in the metal atom or molecules, you can let the electron be away from its original position or its original atom. Okay, that's the meaning of work function. It is the function, it's the energy, okay, with a tiny scale of energy. Okay, work function of selected metals are captured. This is taken from book number 1, right? I captured like this. This is 0, right? It's 0, and please note that the unit of the work function is represented in EV. Okay, EV is the electron volt. I'm not sure electron volt is okay. Electron volt is is this one. Okay, electron volt is a kind of tiny energy unit. Okay, and it's given by if you can remember the value of the charge by electron, it's 1.602 times 10 raised to negative 19, right? That's the value of the electron charge in coulomb. And if you use that value for any energy, it's going to be called 1 electron volt. Okay, electron volt is kind of energy. All right. Yes. Okay. Let's talk about different metals. Silver has the work function as of 4.73, right? Electron volt. Okay, it's quite high, and aluminum has only 4.08. Okay, which is less than the work function by the silver. Okay, you just multiply this value to the electron charge, and you're gonna get the energy in the SI scale. Okay, in joule. And the copper has the work function of 4.7 electron volt. Okay, it's a little bit less than the silver. Okay, copper has weaker bonding force than that in the silver. And ferrite, which is iron for us, right? You can see that iron is quite hard, but it's not the hardest one. In order to remove the energy, the electron from an atom of the iron, you have to put the energy of 4.5 electron volt. Okay, and for sodium, okay, it's not metal. Okay, it's not metal, and it has weaker bonding force, right? Bonding force, and that's why we get here smallest amount of work function. Okay, they just put the energy of only 2.46 electron volt. Okay, then the electron will be away from its original position or from its corresponding atom. All right, and the next one is lead, right? Lead has 4.14. Okay, it's quite strong because it's a kind of metal. And the platinum is a special metal. It has really strong bonding force. It has work function of 6.35 electron volt. And zinc. Okay, zinc has a comparable work function, which is 4.31. Okay, and when the photon energy reaches the work function, you know that photon energy has the formula of Einstein, Planck-Einstein formula, right? It's EHF, right? It's EHF like this one. Okay, in equation number 7. Okay, if you equalize the photon energy to the work function, okay, you can get the relation somehow, right? And if you use this relation, C equal lambda F, okay, and then you would get lambda equal C by F. All right, and if you we have to represent this relation in terms of F. So F is gonna be C by lambda. C is 3 times 10 to 8, right, meter per second. It's a constant, and if you leave this relation to this position, you're gonna get C by lambda, right? C by lambda of H. And if you want to find H, if you want to find lambda, you move lambda to be here, right? In F is C by 5, H C by 5. and that's the result you can obtain in equation number 9. Okay, this is called the cutoff wavelength. Okay, lambda c is cutoff wavelength, and c is the speed of the light. Okay, speed of the light. Probably you may say it's 3 times 10 raised to 8, right? But it's not the case here. It's more precisely, it's almost 3.00. It's 2.99. Okay, but the order on 10 is the same. Okay, it's number 8 is the speed of light in vacuum. Okay, if the photon energy in 7 is greater than the work function, the proton, the electron will be released from its original atom, right? And that's called photoelectron. Okay, the released photoelectron will launch with a maximum kinetic energy as these, right? The difference between the photon energy, okay, this is the photon energy, and the work function. Okay, the smallest amount of energy the metal will allow electron to flow or go out, right? Okay, let an electron volt be an energy unit which is given by 1 eV equal 1.02 times 10 to negative 19. Okay, and now we arrive at the first example. A sodium surface is illuminated. Okay, the surface is now chosen as the candidate. You can take a look at these, right? So sodium is Na here, 2.46, right, for its work function. All right. The sodium surface is illuminated with the light of wavelength 0.3 micrometer. You know that micrometer is 10 to negative 6, right? This one is 10 to negative 6 micro. It's equal to 10 to negative 6. I'm sorry. It's a kind of prefix unit, right? You can use prefix unit to any fundamental unit as you want. All right. Yeah. The energy of each photon. Okay, please calculate the energy of each photon in electron volts. Okay, energy of electron, right? The next one is the maximum kinetic energy of the ejected photoelectrons, and the cutoff wavelength for the sodium, right? That's the third of the last sub-question in this example. Okay, the energy of each photon in electron volt. Okay, so for the first question, we could use E gamma, right? Energy of photon is HF, right? As we have found in this expression, E gamma is equal to HF, right? So E gamma is there, right? And we're gonna substitute everything into that. Sorry. Yes, sir. Like this. Okay. Okay, let's recall the value of Planck constant. Planck constant is provided somehow in the past, right? Okay, h is the Planck constant. It's very tiny value, right? 10 to negative 34. Where is that? Where is the Planck constant? Where is h then? Really at the beginning, right? Here, in equation number 4, right? In equation number 4, now we can go ahead with our story. Yes, sir. Now we go ahead with this example. H is 6.626, right? Times 10 to negative 34, right? And 2 seconds, right? And that's the value for H. And now we will calculate the E gamma, which is the energy of the photon, right? And one thing we need to know is the wavelength, right? As you know, C is equal to lambda f, right? And what we know is solely lambda, so we would be able to substitute f by c by lambda, right? Okay, that's the value for f. And we substitute f to E gamma. So E gamma is going to be h and c by lambda. H is 6.626 times 10 to negative 34. Okay, and our c is 3 times 10 to 8 divided by lambda. Lambda is 0.3. Micro is 10 to negative 6, right? Okay, and you can put it into the calculator, all right? And you will get the result, which is, I don't know. Okay, here. E gamma, 6 point, I don't understand why it's, say 6.26, 6.26. It's gonna need some RAM, right? 626, but 626, but this one. Okay, they use a different value. It's no problem, but anyway, let's compute this result. Where is that? can use the calculator here. Okay, octal. Yes, octal. Okay, so E gamma, E photon, right? E photon, E gamma equals 6.26 626 E minus 34 times 3E8 by 0.3 E minus 6, and the result is 6 point. Okay, it's the same value, 6.26 times 10 to negative 19. Okay, and that's the energy caused by photon. Okay, it's in joule, right? And if you wanna express this value in terms of EV, you have to multiply this value by 1.6 times 10 to negative 16. Okay, all right. The second question is still remaining. The maximum kinetic energy of the ejected electron, right, which is this one, Kmax. Kmax is equal to HF minus phi. All right, and you know that HF is the energy caused by photon, right? It's E gamma minus phi, which is work function for the sodium, right? We are considering sodium will be 2.64 or 46. 2.46, but it's in it's in, I don't understand. It's in EV, right? It's in EV in no. 2.64 is the energy in EV. If you want to work in the SI scale, you have to convert every value into the joule, right? But anyway, 2.46 EV will be this value, 2.46 times 1.6 10 to negative 19. Okay, that's the charge by electron, right? You have to multiply this, and of course the work function is right there. Oh, sorry, the photon energy is right there. So Kmax will be E gamma, but when you make the multiplication or division or summation or addition, please make sure that every term are in the same unit scale, like SI or something smaller. E gamma minus work function, E gamma is 2.4 6, right? Oh no. Yeah. That's the no. Yeah. That's the work function, right? But for us, we need to 2.46. That's the photon energy caused by the source, right? 2.46 electron volts, which is this one, right? 1.6 10 to negative 19. Okay, you have to multiply this one by 1.6, right? And you put the negative, have seen the atomic models, right, by Rutherford and Planck and Einstein have developed the energy of the photon, right? Relation of energy to photon, which is called Planck-Einstein relation. Now, in I don't know, 8 years later, right? Niels Bohr established the relationship between the spectral wavelengths and energy levels. Okay. The photon energy and the work function have been discussed already, and Niels Bohr tried to make the relation between spectrum wavelengths and energy level. He postulated that an electron in an atom can resolve in certain stable orbits. Okay, he imagined that at that time he imagined electrons should have orbits, right? And certain stable orbits. It's not random orbits. Okay, with a definite energy associated with each orbit. Okay, each orbit has its own value for the energy. Okay, without emitting radiation, contrary to the predictions of the classical electromagnetic theory. Okay, it just moves around an atom. Okay, without any electromagnetic wave radiation, which is opposite to the prediction by the classical electromagnetic theory. And an atom emits or absorbs radiation only when the electron makes the transition from one of these stable orbits to another. And at the same time, electron emits or absorb a photon with appropriate energy and frequency according to this relation. Okay, it's like it looks similar to the derivation of equation here. Okay, it's actually the same expression because if you substitute, it's going to be here E initial minus E final, right? The final state, the lower state, and here is the photon energy, right? The photon, a tiny energy packet, and it's the same thing, right? Here you just equalize this term to this one, right? You get EI minus EF. Okay, I stand for initial state, and F denotes the final state of the electron. Okay, and this difference is going to be equal to h, the Planck constant, multiplied by the frequency of the light, whether it's absorbed or it's emitted. Okay. Okay, F is the final energy of the atom after the transition, and I is the initial at the beginning, right? The initial state of the energy of an atom before it moves to another energy level, right? And right now we arrive at figure 18. We have the initial level, right? Energy state, and we have the final energy state. Okay, we have EI and EF, right? Assume that the energy, the electron start from the initial energy, which is the higher state, to the lower state, which is denoted by the final energy state here. Okay, right? An atom drops from an initial level I to a lower energy final level F by emitting. Okay, when you are from the higher energy state, you go to the lower energy state, you need to release the energy, and that energy, the energy you release, it is going to be transformed to light, or it's known energy for the light in terms of photon. Okay, it's going to be the light or photon emitted from this electron transition. All right. The spectrum of visible light includes photons and energies ranging from that's the visible region for human eyes. Okay, please note that from 1.8 eV for the LED right, and to about 3.1 eV for a violet light. Okay, this is the region for human eye that for the observable detection by human eyes. In terms of electron volt, the Planck constant can be converted to another value. Okay, and if you, as of course you know, the Planck constant is represented in Joule per second, Joule times second, right? Because that's the standard unit, right? It's the SI scale, and yeah, it's 6.626 10 to negative 34. And if you want to reduce this tiny amount in terms of electron volts, you just make a deviation to the original value by the electron charge 1.602 10 to negative 19. Okay, you get 4.13 times 10 to negative 15 electron volts. Okay, and S stands for the second too, right? Electron volt second. Okay, that's the another value of the Planck constant in terms of electron volt second. Okay, and Bohr was able to calculate the energy levels and obtain agreement with values determined from spectra. Okay, he developed the formula. He formulated that expression, EI minus EF equal to HF, right? The formula is compared to the actual spectrum of the signal that is emitted from the higher energy state to lower energy state. Okay, let's talk about another example, which is a hypothetical atom has three energy levels, or three energy states. You can see that. The ground state level in levels with 1 electron volt and 3 electron volts. Okay, if you don't completely understand, just take a look at this figure. Okay, the ground level or ground state, okay, is the lowest level, right? And this one is the higher one, which is 1 eV. Okay, 1 eV state, and here is the third level, third energy state level. It's 3 electron volt, right? Find the frequencies and wavelength of the spectrum lines for these atoms. Okay, and what wavelengths can be absorbed by an atom if it is initially in the ground state? Okay, that's the reverse way, right? Reverse way to the first sub question. Okay, frequency and wavelength for the spectrum line of these atoms. Of course, these mean the emission of the light, right? And the emission of the light means that will take place when the electron move from the higher energy state to a lower energy state, right? Because we have three energy states here, 3 eV, 1 eV, and ground state, ground level. You can have three possible emission of the lights, right? The first one is 3 eV to 1 eV, and the second one is from 3 eV to ground state, right? Or 0 eV, you can say it. And that's two possible ways from the 3 eV state, right? Let's talk about 1 eV. There is the only single way, single transition, from 1 eV to the ground state, and we will see, we will consider only the difference of energy, right, between EI and EF. Okay, delta E is the difference of the energy from the initial to the final, okay. So the difference from this one is 3 minus 1 is gonna be 2 eV, right? And if you start from 3 eV to ground state, you would have the difference of energy by 3 eV, right? Because 3 eV minus 0 will remain 3 eV. Okay, let's talk about the second sub question. The wavelength could be absorbed. Okay, if electron absorb the energy, it means that the light propagates and electron will get to the higher energy state, whether it's 1 eV or 3 eV. Okay, so in this case, I think there are three possible cases. Okay, from the ground state to the 1 eV state, and the ground state to the 3 eV state, and the initial state is the ground state. So we have to start from here. Okay, so there will be only two possible cases, from this level to the 1 eV level and to the 3 eV level, right? There will be only two possible cases. That's the energy changes in the second sub question. Let's get into the detail of the first sub question, frequencies and spectrum and wavelength, right? Of this hypothetical atom, right? In the first case, we start from at 3 eV state, 3 eV energy state, right? At the 3 eV energy state, there are two possible way of the light emission or photon emission, right? You have to start from 3 eV to the 1 eV state, right? And you have another case from 3 eV, which is the second case, 3 eV to the ground state, which is 0 eV, right? And from the formula here, you have HF equals EI minus EF. All right. So it means that you have F equal EI minus EF divided by H, right? So let's get into the detail. EI is 3, EF is number 1, so it's gonna remain 2 EV, right? So it's equal to 2 EV. So F will be 2 EV. So you have to multiply it by the photon electron charge, right, in order to get the anyway, you can also use it in electron volt, but you have to use a specific version of the H in EV scale too, right? H in EV scale is 4, right here, right? 4.1356, all right, times 10 to negative 15. Yes, and you put it into the calculator, you're gonna get the 2 by 4.135667696 E minus 15, right? It's gonna be this one, 4.83, okay, is equal to approximate 4.836 times 10 to 14 hertz. Okay, and you can convert it to the wavelength by using the typical formula, right? C lambda F. So lambda is going to be C by F, right? Lambda is going to be Z by F, right? So it's 3 times 10 to 8 divided by 4.836 times 10 to 14, right? And then you will get that value, right? You will get 3E8 divided by this value. It becomes 6.2 times 10 to negative 7 meter. In terms of nanometer, right? It's gonna be 620.35 nanometer. All right, and that's the first wavelength from the 3 EV state to 1 EV state. All right, and the next one is the 3 EV state to 0 EV, right? So now let's talk about this is the F1, right? Let's say this is F1, level 1, F1, 2, right? And now we will talk about second F, right? Second frequency. It's gonna be you know that EI minus EF, right? EI is initial state 3 EV, EF is 0. Right now we consider from 3 EV to the ground state, right? 3 EV state to the ground state. So the difference here is going to be 3 minus 0. So we have 3 EV. 3 EV divided by the Planck constant in EV scales. Let's check whether our solution is 321 is 4836. Yes, it's all right. The frequency is correct. Okay, now the frequency of frequency for the electron from 3 EV to 1 EV to ground state. So this one is 41356 times 10 to negative 15 So if you put it into the calculator, you're gonna get, oh no. Okay, 3 here. Number 3, yes, yes, you will get 7.25 times 10 to 14 hertz. Okay, hertz. And the next one is the lambda, right? Lambda 2 will be C by F2. C by F2 will be 310 to 8 divided by 7.25 times 10 to 14, right? 10 to 14, and yes, you get that. So we get 4.1357 times 10 to negative 7 meter. And yes, in terms of nanometer, you're gonna have it's equal to, actually, it's 413.57 nanometer. Okay, and that's the second wavelength of the photon. Let's check whether it's correct. It's correct or not. 7.2, yeah, 7.254. This one, and the wavelength is 4.13. Okay, 4.13 nanometer or nanometer, and 3 to 1 is 620. Yeah, 600.35. It's all correct. And that's the light from the 3 EV state, right? Now let's move to the lights for the 1 EV state. For the 1 EV state, we have right here 1 EV state number 2, 1 EV state to the ground state or 0 EV, right? So you would have F number 3, right? Will be EI, again minus E final divided by H, which is the Planck constant. EI is the initial state, which is 1. 1 minus 0 is going to be 1 EV, right? Then you have to divide by the Planck constant, which is 4.135610 to negative 15. Okay, and you get this one, right? The one reverse is 2.418 times 10 to 14 hertz, right? And lambda 3 will be lambda 3 will be the wavelength of this emitted photon, right? It's going to be 3 times 10 to 8 divided by 2.418 times 10 to 14, and you will get that 1.24. Okay, 1.24 times 10 to negative 6, and it's in meter, right? And if you please note that it's negative 6. So if you convert it to the nanometer scale, it's going to be 1,240 13.7 nanometer. Okay, and that's all about the photon behavior, photon properties. Okay, now we arrive at the story about the wavelength absorbed by the atom. It's initially in the ground state, right? From the ground state, there will be two possible energy changes, right? The first one is here from the ground state to the 1 eV state, and from the ground state to the 3 eV state, right? So yeah, you just follow the same way, okay? Please note that 1 eV is going to be the levers of these one, right? Levers of this energy transition. So you would get what is that? It's this wavelength. Okay, the wavelength here that could be absorbed will be lambda 3. Okay, which is 1240.7 nanometer. All right, and the second wavelength will be this one, right? From ground state to the 3 eV state. All right, to the 3 eV state, it's gonna be lambda. What lambda? No, it's going to be lambda 2. So it's lambda 2, which is what we have already calculated, 413.57 nanometer. All right, and that's the second wavelength of the photon that could be absorbed by this atom. Okay, from the provided that we start from the ground state. Okay, from this level to this level is 0 eV to 3 eV. So let's check whether our conclusion is correct or not. So the wavelength the atom could be absorbed is, yes, 1240.7 nanometer, and the second one is 413.57 nanometer, and that's okay. That's all right. Now we finished this example, and we go further. Yeah, that's the Bohr model of Bohr atomic models for the hydrogen atom, right? He said because hydrogen is the first element in the periodic table, right? It has only a single proton, single element, single particle in the nucleus, so it's proton. There's no neutron at all, right? And once we have the positive charge, there should be also the negative charge in order to have balance in this atom, right? And of course, there should be only a single electron, and let's say electron moves. This is the linear speed, tangential speed, but actually it moves in a circular way, right? Like a circle here, and there will be centrifugal force F to the center, which is proton. The proton is assumed to be stationary. Okay, it just stay at the center of this atom. Okay, and the electron revolves in a circle of the radius, with radius in here, measured from the center of proton to the location of the electron with speed Vn. Okay, the tangential speed is said to be V with subscript n. Okay, N is the index of the orbit, or let's say it's a quantum number. Okay, and the electrostatic attraction provides the needed centripetal acceleration. Okay, the attractive force between these elements, okay, will be equal to the centripetal force. Okay, all right. The Bohr's model, this one. All right, this one, the Bohr model of the hydrogen atom, includes the following assumption: the Coulomb force produces the electron centripetal acceleration. Okay, the Coulomb force means the attractive force caused by this proton and this electron, right? It's FKQQ by d or r square, right? The distance between those two charges, right? Only certain orbits are stable and allowed for electrons. So electron could be kept or could rotate or could move only in certain orbits, right? And that orbits are stable. Okay, and when electron jumps from a more energetic state to a less energetic state, there will be a light radiation according to 15. That's the equation we have just used for the previous example, right? It's HF EI minus EF here. All right. Okay. The circumference of an electron orbit is an integer of de Broglie wavelength. Okay, circumference means the root along the circular part here, the circumference, right, of an electron is an integer of the de Broglie wavelength. The Broglie wavelength will come later. Based on the above four assumptions, we can calculate the allowed orbit energy, the orbital energy, and the emitted EM wavelength of the hydrogen atom in figure 20. Okay, based on the above four assumptions here. Okay. Two kinds of energies are involved with the electron motion at the end orbit, sometimes known as the quantum state in. Okay, and the electrostatic potential energy, which is denoted by UN, is equal to KE. Okay, KE, and here is the K is a constant. You know that it's a constant from the Coulomb formula, right? KQQ by R, right? And with some derivation on page 948 in this book, you could get the final expression, right? Let's get into detail. KE is the Coulomb constant. Okay, it's 8.9 times 10 to 9 Newton meter square divided by Coulomb square, and that's the Coulomb constant. And epsilon 0 is the electric permittivity of free space, and 8.85 right here. Okay, epsilon 0, and n is the integer, which is usually known as the principal. If you get into the detail, it's called principal quantum number. Okay, the main quantum number. There are four quantum numbers actually. Okay, that's the two major energies that could happen to electron. The first one is electrostatic from the Coulomb formula. It's a force caused by two charges, and the second one is the kinetic energy, because the electron is moving, right? So it's 1 by 2 me, the mass of electron, right? And the E is the electron charge, right? You substitute everything. you could get this expression. You could observe that they are quite similar to each other, right? It's this one here is the number 4, this one here is the number 8, n square and h square, right? And e with a power 4, right? The power 4. Ke is 9.8, 8.9, sorry, 8.9, and epsilon 0 is electric permittivity. N is the principal quantum number. Okay, you could see that this one is the negative version of this one, and half of the electric potential energy, and the total energy of electron. Okay, you just make the combination of these two values, you get this value. Okay, to just add this term to this term, you n plus kn, you get 1 by epsilon 0 and 8 n square h square MeE4. And now we have a new variable, which is h slash. Okay, h slash is the reduced Planck constant. It's a circular version of the Planck constant. You know that h is the typical Planck constant, right? But if you divide it by 2 pi, okay, this is going to be the radius, the circumference. If you divide it by 2 pi, okay, you would get h slash, which is 1.05. Everything is the same. Okay, you just divide it by 6, blah blah blah, 6.28, blah blah blah, which is less than these numbers. That's why it's gonna remain 1 blah blah blah. Okay, 10 to negative 34 Joule second. The negative sign in 25 means the kinetic energy is smaller in magnitude than the potential energy. Okay, and if all the constant in 25 are substituted here, you will arrive at simple expression, which is only negative 13.6 in n square here. All right, and please note that actually the unit of this one is going to be Joule, right? And we convert it immediately to the simple or appropriate scale, which is electron volt, right? Once we talk about atomic models, the most appropriate scale of the energy is going to be electron volt. Okay, we don't talk about Joule at all. All right, Joule is the general scale of energy or work. Okay, in many physics scenario, but for atomic model, for atomic scale, we're going to use electron volt as the appropriate and more suitable energy scale, which is 13.6 by n square, right? If the electron is completely removed from the hydrogen atom, the orbit energy becomes E epsilon, okay? You know that n is the principal quantum number. If n is number 1, it's going to be 1 square, right? It's going to remain number 1, or here at the denominator. And after the division, you would get minus 13.6. So the closest level to the nucleus, you would have negative 13.6 electron volts, okay? Please note that the energy here is negative because it's negative from this equation 25. So it means that the kinetic energy is smaller than the potential energy. Okay. The movement, the energy caused by movement of the electron is less than the potential energy. And the next thing is electron is completely removed from the hydrogen atom. It means that the orbit or the state of electron orbit is very, very far from the nucleus, and that state would take n to be very, very large value, right? So n is going to be like some kind of infinity. And when n is infinity, you will get negative 13.6 by something very large, and it's going to remain 0 finally. So we have E infinity, which is the distance of the location, which is very, very far, extremely far from the nucleus of that electron or the hydrogen atom, will remain 0 electron volt or 0 joule too, right? The difference between energy at the smallest orbit and at the removed orbit will be E1, right? Please note that when we are extremely far from the nucleus of that hydrogen atom, we have energy state as E infinity, right? And the difference of this one is going to be minus E1. E1 is the first energy state of the in that hydrogen atom. So you have 0 minus 13.6 eV, right? You will end up with the positive 13.6 eV, okay, as the outcome. So this is known also as the ionization energy of the hydrogen atom. Okay, so the range, okay, the maximal difference between energy state of the hydrogen atom. The third assumption by Bohr leads to the wavelength of the EM radiation, and we could get HF, right? HF, which is approximated as E initial. Okay, you start from. Please note that this is if this is the first state of the electron orbit, the state which is closest, okay, and the most possible closest state to the nucleus. So that's the 13, right? In for whatever initial state to the final state, you start from Ni to Nf, and the difference of the energy is going to be released in terms of photon is the difference of the Ei and Ef, right? Ei minus Ef, right? Ei is the first term, which is negative. Ef is the second term, which is also negative. So if you arrange this thing, right, of course, Nf has twice the negative term is going to remain as positive term, right? Positive quantity. It's going to stay first at the beginning. And here we have a single negative. It's going to stay as the second term. So Ni stay at the second position. And both terms have the same 13.6 constant. So we move it to this one, right? 13.6. Okay, and F is the quantum number or integer of the final state. And I is the quantum number of or integer of the initial state, and Ni is greater than Nf. Okay, in initial it should be greater than final. Okay, you should start from lower state to the higher state. Okay, let's say this is the Ni. And here is Nf, okay. In this case, you go from this, right? And yeah, that's the way we could do with that's the way we could do with this expression in I and Nf, right? So F is C by lambda. If we substitute F equals C by lambda into this expression, we're gonna get CH and lambda, and after that you get 13.6 on the right hand side, right? Then we solve this expression for lambda, right? We solve this one for lambda is gonna be 1 by lambda, and we move h to the denominator of 13.6. We move z also to the denominator of 13.6. So that constant is known as the Rydberg constant. Okay, this person, I think if I can remember properly, he is a Swedish person, Swedish physicist. Okay, and the constant has unit of reciprocal of the meter. All right, the Rydberg constant, and if you get into the detail, the Rydberg constant could be found from this one. Okay, and whether it's in the h// term or the typical Planck constant. But anyway, don't worry about that. Rydberg constant will be provided here, which is 1.0973. Okay, and that's the Rydberg constant. Okay, equation 31 is known as the Rydberg formula, but actually it's derived from the Bohr expression. Okay, if you pay attention to the wavelength of the photon, so you would get this. Okay, and yeah, NF should be greater than NF, otherwise you get a negative value here, and it's impossible to have the negative value for the wavelength, right? Wavelength should have positive value. Once we put the constant, okay, we get the Rydberg as this value. You may not need to remember this this constant. Okay, if we have an exam, this value is going to be provided additionally. Okay, you don't have to worry about the you need to remember that or not. Okay, and now the time is over. We will continue the example on this Friday lecture. All right. เวลาก็หมดแล้วนะครับ 19:00 นะครับก็วันเลคเชอร์สำหรับการชดเชยก็หมดไว้เพียงเท่านี้นะครับก็บ๊ายบายครับสวัสดีครับbye bye. See you on Friday morning lecture, right? Stop this one.